All right, folks, welcome back. It's good to see you all back for the second day of class. So last time we did a quick review of fluid mechanics. We talked about your top 10 concepts from fluid mechanics. We talked about things like Reynolds transport theorem, hydrostatic law, conservation of energy, Bernoulli's equation, all that good stuff. We also talked a bit about intrinsic properties of water. So these are properties that you're going to need to keep in mind when doing problems for this class. So what are a couple properties of water that we mentioned last time?
Density.
Density, very good. What else? Viscosity, very good. So you'll need that when doing problems related to frictional losses in pipes. And how about one more? Yes. Yes, modulus of elasticity. So that characterizes the compressibility of the fluid. So these are properties that you need to keep in mind. What quantity do most of these properties vary with? Temperature, right? So keep in mind when you're doing your homework problems that sometimes these properties will vary with temperature, and so keep track of those temperatures at which the problems are being solved. So we ended our lecture yesterday talking about pipe flow versus open channel flow. And the key idea that I wanted to convey to you was that in pressurized pipe flow, we basically assume that the fluid is incompressible and that the pipe is completely full of water. So if the pipe is completely full of water, that means that the flow rate into the pipe is always going to be the same as the flow rate out. That's going to affect how we solve some problems in this class. For open channel flow, we have a conduit with some free water surface. So the conduit may not be full of water. The hydraulic geometry may change over time. So if the discharge increases, you might get a different shape. So for instance, if the water level rises in this conduit, you're going to have a slightly different shape than if the conduit is less full. And also it's possible for the flow into the control volume to not be equal to the flow out, because it's possible for water to accumulate or empty out over time in your control volume. So pressurized pipe flow is going to be the first half of this class, and open channel flow, which is a bit more complicated of a case, that's going to be the second half of the class. All right, any questions on pressurized pipe flow versus open channel flow or any of the concepts we talked about on Tuesday? Nope. All right. So today we're going to be covering three important topics. So first, I want to just review discharge and velocity in pipes. So a review of some material from fluid mechanics. And then I want to talk about the two principles that are going to form the basis for the rest of this class, really. So almost every problem that we're going to do and almost every equation that we're going to use boils down to conservation of mass and conservation of momentum. So I'm going to take it slow today and go through each of these concepts in detail. I'm going to do a full derivation of the conservation of mass, full derivation for the conservation of momentum for the case of flow in pipes. So you can get a good intuition for how these concepts work. Let's start by reviewing discharge in pipes. So I started to talk about this at the end of class yesterday, but didn't quite finish. So let's say we have some pipe with water flowing in it. So there's some flow rate through this pipe. And generally, when you have flow going through a pipe, you'll have a velocity distribution. In this case, we have this nice parabolic velocity distribution with the largest velocities towards the center of the pipe, the smallest velocities towards the wall of the pipe. So if we want to compute the total discharge through the pipe, what we can do is essentially break up our pipe into a series of areas. So in this case, I'm breaking up the pipe's cross-section into areas starting from the center of the circle and moving outwards. And for each of those areas, there's some velocity associated with it. So we can compute the discharge by multiplying the velocities for each of these respective areas and adding them up. In the continuous case, we can compute that discharge by performing an integral, where we are basically multiplying the velocity by some infinitesimal area and then adding up all of those infinitesimal areas together. So I started with an example. At the end of class yesterday, we have a circular pipe with a radius of r equal to 1 meter, and it's carrying water with the following velocity distribution. So here, r starts at the center of the pipe and moves outwards to the wall. So little r is a variable. Big R is the full radius of the pipe, which is equal to 1 meter. The velocity distribution is this parabolic velocity distribution. So v as a function of our distance from the center r is equal to 1 minus r squared meters per second. So we have this nice functional velocity distribution. You can see just by evaluating this function that at the center of the pipe, the velocity will be 1 meter per second, where r is equal to 0. And at the wall of the pipe, the minimum velocity will be equal to 0, right? Because 1 minus 1 squared is equal to 0. So if we want to compute the total discharge, we can take this velocity function and integrate it over the entire area of the pipe. So the most natural way to do that is using polar coordinates. So let's go ahead and perform that integral. It's going to be very similar to one of the homework problems you'll need to solve. So we have that the discharge Q is equal to the integral of v times dA. So that's the velocity times some infinitesimal area associated with that velocity. And we're integrating over the entire area of the pipe. So the most natural way to do this for a circular pipe is in polar coordinates. There's various ways we could break up the pipe if we wanted to. We could break it up into little rectangles. What I'm going to do is I'm going to integrate it in polar coordinates. So we're going to integrate first from the center to the wall, and then we're going to integrate around the circle. When we do that, our infinitesimal area will take the form of this little polar rectangle with the following dimensions. So the width of this little polar rectangle is going to be dr. The length is going to be equal to the arc length, which is the radius times the change in the angle over our polar rectangle. So this, if you multiply the width by the length, you get dA. So let's go ahead and perform this integration. I started this last time. So we're integrating in polar coordinates. As I mentioned, we're going to integrate first from the center to the wall, and then we're going to integrate around the circumference of the pipe. So we're integrating first dr and then d theta. We're integrating our function VR times dA. And note that dA we have is equal to r times dr times d theta. So this quantity here, this is dA. This quantity here is our velocity function. So for dr, what are our limits of integration going to be? 0 to 1, right? Because we're moving this way from 0 to big R is equal to 1. So our limits of integration for that inner integral are going to be 0 to 1. And what about our limits of integration for d theta? 0 to 2 pi, very good. So we are integrating around the entire circle. So we'll get an integral from 0 to 1 in terms of dr, and then 0 to 2 pi in terms of our voyage around the circumference of the circle. All right, so we can go ahead and just plug in our expression for VR. We're integrating 0 to 2 pi, 0 to 1. In our expression for VR, we have a nice functional form for that velocity distribution. That's 1 minus r squared time to r times dr times d theta. And if you go and evaluate this integral with these limits of integration, you should get a value of about pi over 2 cubic meters per second. So I'm not going to do the entire process here because it's very similar to a homework problem that you have. I will leave the integration as an exercise for you, but that's how we would compute the discharge through a pipe if we know explicitly what that velocity distribution is. For laminar flow, we often can get an explicit expression for that velocity distribution. All right, any questions on this problem? Yes?
Just to confirm, we do the integration of the inside one first and then do that.
You can change the order of integration if you want, as long as you're just making sure that that exchange of the limits of integration is valid. So yes, you can integrate the angle first and then the radius. Any other questions? All right, so that's how we would compute the discharge if we have a velocity distribution. For most of the cases in this class and most of the practical cases that you'll be working with, we won't be using the full velocity distribution in the pipe. Rather, we'll be working instead with the mean velocity of flow. So this is what we're primarily going to be using for the rest of the class. The mean velocity of flow. And in this class, I will be referring to the mean velocity of flow with the variable u. So this is a u as in u. And the mean velocity of flow is defined as follows. We have that the discharge is equal to the mean velocity of flow times the cross-sectional area. Okay, so it's the velocity such that the discharge is equal to that velocity times the cross-sectional area. Or equivalently, the mean velocity of flow is equal to the discharge divided by the cross-sectional area. So let me just be explicit here. This Q is the discharge. So this would be in units of something like cubic meters per second. This area, this is the cross-sectional area. This might be in units like square meters. And this U is our mean velocity. Which would be in units of something like meters per second. So in almost all of the cases in this class, we'll be dealing with the mean velocity of flow instead of the full velocity distribution. That's probably how you'll be working with the velocity in practice as well. So are there any questions on the definition of the mean velocity of flow? All right, let's do a quick example just to reinforce. So let's say we have a pipe and we want to compute the mean velocity of flow given the dimensions of the pipe along with the discharge. So we have some pipe. There's a discharge of 25 cubic feet per second moving through the pipe. And let's say we know the diameter of the pipe. So the diameter of the pipe, let's say it's just equal to 5 feet. This is a pretty big pipe. All right, so we know that the mean velocity of flow is simply equal to the discharge divided by the cross-sectional area. So how can we express the cross-sectional area of the pipe in terms of the variables that we know? What's an expression for the cross-sectional area in terms of the diameter? Yes, so if we evaluate that expression, we should get pi times d squared divided by 4. So the 2 gets squared. So remember this formula for the area of a circle. You're going to be using it a lot. Pi d squared over 4. So our mean velocity is equal to Q, the discharge, divided by pi d squared over 4. I'll just put parentheses here to make it clear where the denominator should be. And if we simplify this, we get 4Q divided by pi d squared. Let's go ahead and substitute in the values that we know. So we have 4 times 25 cubic feet per second divided by pi divided by the diameter squared. So that is 5 squared. I'll just write the units in here, 5 feet squared. And if we evaluate this expression, we should get u, the mean velocity of flow, is equal to 1.27 feet per second. All right, so that's not so bad. Let's do a slightly more complicated example. Give me a second to finish writing. So let's say instead of a pipe of constant diameter, let's say that we have a nozzle. Say we have a nozzle that decreases in diameter. And the diameter at the upstream end of the nozzle is equal to 5 feet. So I'll call this D1 is equal to 5 feet. The diameter on the downstream end of the nozzle is going to be D2 is equal to 1 foot. And just like before, let's say at the upstream end, there is a discharge of 25 cubic feet per second. All right. And what I want to do is compute the mean velocity of flow, which I'll call U2 at the downstream end. Okay, so first of all, do we know what the discharge is at the downstream end of the nozzle? Yes. What is the discharge at the downstream end of the nozzle? Yes. It's the same as Q1. So remember that we have a pressurized pipe or a pressurized nozzle in this case. The nozzle is completely full of water, so the flow in has to equal the flow out. So we have that the discharge at the downstream end is also equal to 25 cubic feet per second. So we have Q1 is equal to Q2 is equal to Q, which is equal to 25 cubic feet per second. So then the velocity of flow at the downstream end is just going to be U2 is equal to Q divided by A2. So this is just going to be using the same expression we had on the previous problem. This is going to be 4Q divided by pi d2 squared. And if we evaluate this expression, we get a value of 31.8 feet per second. So the velocity increased from about 1.27 feet per second to 31.8 feet per second at the downstream end of the nozzle. So that's something you'll often see with fluid problems like this, is that a small decrease in the diameter or a relatively small decrease in the diameter can result in a very large increase in the velocity. All right. By the way, what concept did we use to infer that the flow rate in has to equal the flow rate out? What physical concept did we use? Yes.
Conservation of mass.
Conservation of mass, very good. So that brings us to our next topic, conservation of mass. We're going to look at conservation of mass in more detail. So for the next probably 40 minutes or so, I'm going to derive conservation of mass and conservation of momentum in detail for a fluid control volume. I'm going to show you exactly where these two equations come from, and I'm going to help build some intuition. Does anyone know what another name for conservation of mass is? Did you? Continuity, very good. So there's another name that I'll be using to refer to conservation of mass throughout the class. So it's hard to overstate how important conservation of mass and conservation of momentum and consequently conservation of energy are going to be for this class. So I want to take some time to go through them in detail. Pretty much everything you're going to be doing in this class boils down to conservation of mass and conservation of momentum in some way, usually through the energy equation, which will show how to derive from the more fundamental conservation of mass and momentum. So these are the most general equations that will essentially always apply for a fluid system. So no matter what, if you're confused about a particular problem, you can always go back to think about them in terms of conservation of mass, conservation of momentum. Those two concepts will always apply. So let's go ahead and look at conservation of mass for a fluid control volume. I'm going to draw a pipe here. For this case, I'm going to look at the more general case where the pipe doesn't necessarily have to be full. But we'll talk a little bit about how this simplifies in the case where the pipe is flowing completely full. Okay, so there is the profile view of the pipe. And I'm going to draw a cross section of the pipe as well. Okay, so let's consider the conservation of mass over some discrete time interval. What does the conservation of mass or continuity state just in plain English terms? Yes. Under what case does the mass in have to equal the mass out? It's not necessarily always the case, right? Yes. That's also true. Thinking about just how to express this mathematically, though, so we have some mass flow rate is coming into this control volume, some mass flow rate is coming out. Is it necessarily always the case that the mass flow rate in will equal the mass flow rate out? What's a more general way we can express conservation of mass? And remember, I'm talking here about a conduit in which the pipe isn't necessarily completely full. So let's say it's just halfway full like this. What's a more general way we can express conservation of mass? Let's say we're thinking about it over some time interval.
Mass in minus mass out equals change in value.
Yes, that is correct. So the mass flow rate in minus the mass flow rate out has to equal the rate of change of mass within the control volume. So let's just write that out in plain English. This is the most general case. The conservation of mass states that the rate of change of mass within our control volume has to equal the mass flow rate in minus the mass flow rate out. So this is another way of stating that mass can neither be created nor destroyed in the system. The rate of change of mass within the control volume with respect to time is equal to the mass flow rate in minus the mass flow rate out. So let's go ahead and draw that out. Bless you. So here's our profile of the pipe. Here is our cross section. And let's say we have some mass of fluid in our control volume at time t. I'll write that as mass at time t. My t's kind of look like pluses, so just keep that in mind. So we have some mass at time t. We are looking at this system over some discrete time interval. So let's say we have some discrete time interval delta t. So we start with some mass t at time t, and then we go forward in time. And maybe the mass within our system changes. Maybe the water rises up to this level here. And so the mass of fluid at that time we can call mt plus delta t. So that's the mass at time t plus delta t. Now here this is mass. This here is mass at time t. Okay, so we have some mass at time t. We have some mass a little bit later, mass at time t plus delta t. And we have some mass flow rate in, which I'll call m dot in. We have some mass flow rate out, which I'll call m dot out. Similarly, over here, I'm just going to draw it on this cross section as well. So we have this blue area here. This corresponds to our mass at time t. This red shaded area here. This corresponds to our mass at time t plus delta t. Okay, so we have a mass flow rate in, a mass flow rate out, and we have a mass at time t and a mass sometime later at t plus delta t. So let's go ahead and write out, yes?
To confirm that dot on top of the m, is that the rate?
Yes, it means the mass flow rate. So I'll write that out. So note that this is mass flow rate. So let's write out our conservation of mass mathematically in terms of these variables we have defined here. So we have the time rate of change of mass has to equal the mass flow rate in minus the mass flow rate out. We can express that as follows. So we have the mass at time t plus delta t minus the mass at time t divided by our time increment delta t has to equal the mass flow rate in minus the mass flow rate out. All right, so let's go ahead and simplify this a little bit. So let's say we want to express this mass in terms of the volume. We can write that the mass at any time is equal to the density of the fluid times the volume. This is the volume. This is the density. And we can write that the mass flow rate is equal to the density times what quantity? Q, very good. So the mass flow rate has to equal the density, which is the mass per unit volume, times the flow rate, which is volume per unit time. Okay, so the mass flow rate is equal to the density times the volumetric flow rate. This is the mass flow rate. So we can rewrite this expression using those two variables. We have density times the volume at time t plus delta t minus the volume at time t all over our time increment delta t. Is equal to the density times Qn, that's the flow rate into the control volume, minus the density times Q out, the flow rate out of the control volume. Oh, I should probably write here, this is the density coming in, and this is the density coming out. If we're talking about water in a typical pipe system, how could we simplify this expression a little bit? If we're assuming that it's essentially incompressible. Sorry? Yeah, the density is not really going to change, so we can just remove the density. All right, and let's say we have some dimensions for our control volume that we can use to express the volume. So let's say we know the length, the length of our control volume is, I'm going to call it delta x. And let's say we also know the cross-sectional area of the fluid. So that will be this cross-sectional area here. This will be A at time t. And this cross-sectional area here for time t plus delta t. Okay. Similarly, this cross-sectional area in red is the area at time t plus delta t. This cross-sectional area in blue is the area at time t. So how can we express the volume, V, in terms of the cross-sectional area and the length of the pipe? Yes. Yes. So the volume of the fluid is going to be equal to the cross-sectional area times the length of our control volume. So this allows us to simplify. And this entire expression here will become delta x times the cross-sectional area at time t plus delta t minus the cross-sectional area at time t divided by our time increment delta t is equal to q in minus q out. We're almost there. Any questions so far? Yes.
We canceled out the density because you said it doesn't change due to incompressibility. Was that only for like a full pipe or also for like both?
That's going to be for both. We'll show what happens. So right now, this is for the full case where it might not be flowing full. Incompressibility will apply for both of those cases. The case where you'll get compressibility is usually with gases, which we won't be talking about in this course. But for liquids, you can usually assume that it's basically incompressible. All right, let's move on. So what I'm going to do is I'm going to take this entire expression, I'm going to divide through by delta x. So we'll end up with the area at time t plus delta t minus the area at time t divided by delta t plus, I'm going to take this and I'm going to move it over to the left-hand side. So it'll become Q out minus Q in on the other side. So we'll get A at time t plus delta t minus AT divided by delta t plus quantity Q out minus Q in over delta x is equal to 0. And now what I'm going to do is I'm going to take the limit as delta t goes to 0 and as delta x goes to 0. And when we do that, we get the following differential equation. So we take the limit as delta t goes to 0. This becomes dA by dt. And as we take delta x as it goes to 0, this becomes dq by dx. And this is always going to be equal to 0. So this is our general expression for conservation of mass or continuity. So this will always apply. And it looks like a scary partial differential equation with dAs and dQs and dTs and dXs, but it's stating something relatively simple, okay, which is that the mass flow rate in minus the mass flow rate out is equal to the change in mass within our control volume. So let me break down what each of these terms means. This dA by dt, this refers to the change in mass. And correspondingly, the change in volume within our control volume. So the dA by dt is basically referring to the change in volume within our control volume over time, or the change in mass within our control volume over time. The dq by dx, this refers to the mass or volume flux through the control volume. So in other words, this is flow out minus flow in. And so basically what this equation is stating is that the rate of change of volume, the rate of change of fluid volume within our control volume has to equal the volumetric flow rate in minus the volumetric flow rate out. So this is the most general equation for continuity for conservation of mass. So as I mentioned, this applies to both pressurized pipe flow and open channel flow. How can we simplify this equation here for the case of pressurized pipe flow? So let's go through each of these terms. Look at for pressurized pipe flow. Okay, what about dA by dt for pressurized pipe flow? Remember that this refers to the change in volume of the fluid within our control volume, the change in the cross-sectional area with respect to time. So what does this term equal for the case of pressurized pipe flow? Zero, right? The pipe is always flowing completely full, so the change in cross-sectional area of the fluid within the pipe, the change in the volume within the pipe is always going to be equal to 0. What about dq by dx? Remember, this refers to the mass flux through the control volume. So if we go back to our equation, right, if dA by dt is equal to 0, what does dq by dx have to be equal to? Also 0, right? So the flow rate in is equal to the flow rate out. In other words, the net mass flux through the control volume is equal to 0. Okay, so dq by dx is also equal to 0. All right, any questions on that derivation? Yes.
I'm a bit confused about the partial derivative of A over T.
Mhm.
Why is it mass and volume? What is mass or volume?
Because the density is not changing, so the density is just a constant. We can basically say that the rate of change of mass and the rate of change of volume are equivalent up to some constant factor. Yeah. If this was a compressible fluid, the expression would be a little bit more complicated because you have to account for the change in density. But for our case, for an incompressible fluid, the two are equivalent. So volume change and mass change are equivalent up to a constant factor.
This change of mass or volume?
Yeah, so for a constant density, conservation of mass and conservation of volume would basically be the same. Good question. Hey, any other questions on this derivation before I move on? All right, so next let's move to conservation of momentum. So this is going to be a bit trickier. I'm talking about conservation of linear momentum in particular here. What this basically boils down to is we're going to apply Newton's second law to a control volume of fluid. So this is basically the same as Newton's second law, which you'll probably remember from Physics 101. Or from dynamics, what equation did you use to apply Newton's second law? Or what does Newton's second law state in plain English? Very good. So the sum of forces acting on a body is equal to the mass times the acceleration. So this is the form of the equation you probably applied in physics and dynamics. It's not the way that Isaac Newton originally stated conservation of momentum or his second law. Does anyone know how Newton's second law was originally formulated? Yes. Yes, very good. So the way the law was originally stated, and kind of the more general definition, is that the sum of forces acting on a body is equal to the time rate of change of the momentum. So this is momentum in this bracket here. M is the mass, U is the velocity. And the sum of forces acting on that body has to be equal to the time rate of change of momentum. So let me also write that out in plain English. This is the time rate of change of momentum. And the left-hand side here represents the sum of the forces acting on the body. So in physics and dynamics, you probably applied Newton's second law to a solid body. Here we're going to try applying the same principle to a fluid body and see what comes out of that. All right, so let me draw a fluid system. So I'm just going to draw fluid in a pipe. And for this case, I'm going to have the pipe flowing completely full. It turns out it's not really going to matter in terms of the force balance. So here's our pipe. And let's say it's flowing completely full of water. Got this blue line here. This is the water in the pipe. Okay, and I want your help. So what are the forces acting on the fluid in the pipe? I want at least three. Let me draw this line a little better here. What are some of the forces acting on the fluid in the pipe?
They're normal.
Yes, so there will be a normal force acting from the pipe wall on the fluid. So for our case, we're interested mostly in the forces acting in the direction of flow, because we're interested in how the momentum of the fluid changes with respect to the direction of flow. So what force in the direction of flow would the normal force give rise to? Friction, right? So there will be a frictional force exerted by the pipe wall. Okay, I'll call that F sub F. And we can write the frictional force explicitly in terms of the mean shear stress. So it's going to be negative tau, where tau is the mean shear stress, times the wetted perimeter P. So that is the perimeter that the water is in contact with, times delta X, where delta X is the length of the control volume. So let me write that out for you. This tau is the mean shear stress. P is the wetted perimeter. i.e. the perimeter over which the shear stress is being applied, and then the delta X is the length of our control volume. And let me just write that length out explicitly. This length is delta X. Okay, so very good. That's one force we have acting on the fluid in the pipe. I forgot to mention, this pipe is actually at an angle. So say in general, we're going to be at some angle theta with the horizontal. Okay, so what are some other forces that are acting on the fluid in this control volume? Gravity. Very good. So we have the weight of the fluid itself. So the weight of the fluid, W, this is going to be equal to the mass of the fluid times the acceleration due to gravity. And what is the component of that gravitational force with respect to the direction of flow? I'll call it F sub G for gravitational force. It'll be M times G times something. Close. It'll be sine theta. I always used to get that mixed up in physics 101. But the gravitational force in the direction of flow is going to be M times G times sine theta. And just to make a note, this is the direction of flow. All right, so we've got two forces. We've got F sub F, this is the frictional force. We have F sub G, which is the gravitational force. There's one more force we need to account for here for pressurized flow in a pipe. What's the last force we have to account for? Yes.
I'm not sure if it has a name, but isn't it due to the pressure acting on the control volume on both sides?
Yes, so I'm just going to refer to it as the pressure force, the net pressure force. So we have some pressure acting on the upstream end. So I'll call that FP1. This is equal to the pressure at the upstream end, P1, times the cross-sectional area at the upstream end, A1. We also have some net pressure force at the downstream end acting in the opposite direction. This is going to be FP2. It's equal to the pressure at the downstream end times the cross-sectional area at the downstream end. So FP, our pressure force, is going to be equal to FP1 minus FP2. Okay, so it's the net pressure force. All right, and those are the major forces that we're going to need to account for. You may run into some other forces if you're looking at things like minor losses, which we'll talk about a little bit later, but these are the major ones we have to account for. So now that we have our force balance, let's go back to Newton's second law. And I'm going to write it out. We have that the sum of forces is equal to the time rate of change of momentum. So let's take a look at this momentum term in more detail. So we have our net rate of change of momentum. From everybody's favorite theorem, Reynolds transport theorem, we have that this net rate of change of momentum is equal to the sum of two quantities. The first is the rate of change of momentum within the control volume. And the second is the net momentum flux through the control volume. So I'm going to, again, break this down. We're going to look at the net rate of change of momentum over a discrete time interval. So I'm going to take this continuous rate of change, and I'm going to approximate it over some discrete time interval delta t, because I think it just makes it easier to think about. So first we have the net rate of change of momentum within the control volume. So this will be equal to the mass at time t plus delta t times the velocity at time t plus delta t minus the mass at time t times the velocity at time t, all divided by our discrete time interval delta t. So that is the internal rate of change of momentum within the control volume. And then to that, we need to add the momentum flux through the control volume. So this is going to be the mass flow rate out times the velocity out minus the mass flow rate in times the velocity in. Any questions on this? Yes.
You tell me what flux means again, instead of like a change, basically.
Yeah, it's kind of like think of like a quantity moving through some area. So it's just referring to the transport of that quantity through that area, or the flux of that quantity through that area. So in this case, the surface over which we're looking is the cross-sectional area of the boundary of the control volume. So yes, it's the momentum transport through that face. And remember that our mass here is equal to the density times the volume, which is equal to the density times the cross-sectional area times the length delta x. And similarly, just like before, we have that the mass flow rate is equal to the density times the volumetric flow rate. So let's apply these two simplifications. Oh, yes. Yes, yes. So for all of these, we're just looking at the mean velocity of flow. Yes, good question. Yes.
Sorry, can you explain? I'm just trying to wrap my head around what net momentum flux means.
Mm-hmm. So you can kind of think of momentum as a quantity that can be advected in the same way that like some, you know, like some quantity within the water can also be transported. So basically it's just there's some momentum is being transported through the fluid volume. And from Reynolds transport theorem, the rate of change of momentum within the control volume plus the momentum flux has to equal the sum of forces. So for the rate of change of momentum within the control volume, you can kind of see what it is here. So it's the mass at the previous times at the next time step times the velocity at the next time step minus the mass times the velocity at the previous time step. The flux through is basically the momentum that's leaving that control volume minus the momentum that's entering the control volume at any given time step. This might just be something to so I'll try to come up with like a visual in the next class to kind of convey this better. But for now, I'd say to just get used to it, and then understanding will eventually come from working with it. Yeah. So good question. So I'll come up with some kind of visual to help explain this better. All right, so let's take this expression and use the density to try to relate it in terms of the flow rate and the dimensions of the control volume. So we have that our rate of change of momentum for our control volume is equal to the density times the length times quantity cross-sectional area at time t plus delta t times the velocity at time d plus delta t minus the cross-sectional area at time t times the velocity at time t divided by delta t plus the density times Q out, U out minus Q in, U in. So that's the discharge out times the velocity out minus the discharge in times the velocity in. So we can simplify this term here and also this term. What is the cross-sectional area times the mean velocity? Q, very good. So this here becomes the density times delta x times quantity Q, the discharge at time t plus delta t minus Q at time t divided by delta t plus the density times Q out, U out minus Q in, U in. So this is the left-hand side of our Newton's second law. So this is the, sorry, right-hand side. This is the rate of change of momentum with respect to time. And we can take this expression here and set it equal to our force balance. Let's go ahead and do that. We'll have our full expression for conservation of momentum. Okay, so I'm going to use the left-hand side here to represent the change in momentum. So we have the density times the length of the control volume times the discharge at time t plus delta t minus the discharge at time t divided by delta t plus the density times q out, u out minus q in un. We set this change in momentum equal to our sum of forces. So first, let's look at the pressure force. So I'm going to write this as Pn times An. So that's the pressure at the upstream side times the cross-sectional area at the upstream side minus P out, A out. So that's the pressure at the downstream side times the cross-sectional area at the downstream side. We're going to add to this the gravitational force. So this is G times the density times the cross-sectional area times delta x times sine theta. So this entire expression here, this is m. So this is gm sine theta. And then to this, we're going to add our frictional force. So as I mentioned before, this is going to be equal to negative tau times the wetted perimeter times the length of the control volume. So it's negative because friction always acts in the direction opposite to the flow. Okay, we're almost done here. What I'm going to do is I'm going to divide through by the density times the length of the control volume. So if we do that, we get Q at time t plus delta t minus Q at time t divided by delta t plus quantity Q out, U out minus Q in UN divided by delta x is equal to the acceleration due to gravity times Pn An minus P out A out divided by the acceleration due to gravity times the density times delta x plus quantity G A sine theta plus quantity negative tau, the mean shear stress, times the wetted perimeter divided by the density. All right, we're almost there. I'm just going to make a couple of simplifications. I'm going to move quickly just to the next page so I can show where these simplifications come from, but I'm going to simplify the gravitational force term and also the frictional force term. Oh, yes, for who's,
Oh, is that a divided sign or is it, I'm kind of confused.
where?
Is that a division sign or is that the?
Big line in the middle.
Oh, no, no, no. Yeah, that's just separating these two sections. I'll get rid of that. Yeah, that would be a,
That's the new formula.
yeah, yeah. So Let me just, I'll put this in yellow here to show that it's not a division. Is that the same question you had? No. Yes, I will. Yeah, I'll do it definitely by this week. All right, so I'm going to make two simplifications here. All right, the first thing I'm going to do is I'm going to simplify the sine theta term. We'll use what's called the small angle approximation. And basically what this states is that for a small enough angle theta, let's say we have a triangle like this. Some angle theta. We have this leg is equal to delta z, this leg is equal to delta x, and the hypotenuse is equal to delta z plus delta x, square root of delta z plus delta x squared. If the angle is small enough, so if the angle is small, which is usually the case when you have pipes or open channels, the angle will be very small. Sine theta will be approximately equal to the tangent of theta. And thus sine of theta is approximately equal just to delta z divided by delta x, which I will call the bottom slope. So basically this is for the case where the length delta x is almost the same as the hypotenuse. And this will generally be the case for pipelines and open channels, pretty much all the systems we'll be looking at in this class. So in other words, delta x is approximately equal to the square root of delta x squared plus delta z squared. So we have that sine theta is approximately equal to the bottom slope. And then I'm going to define something called a friction slope. We'll be using this a little bit later when we talk about frictional losses. But the frictional slope we'll define as negative tau times the wetted perimeter divided by the density. So it's just going to be equal to the final term in our previous equation. So here, this term here becomes G times A times the bottom slope. And this term here becomes the friction slope. So if we take this equation and just like before, we take the limit as delta t goes to 0 and as delta x goes to 0. So we're going to take limit as delta x goes to 0 and as delta t goes to 0. What we'll get is the following, and this is the general form of the conservation of momentum equation. We'll get that 0 is equal to dq by dt. So this comes from this first term here. This becomes dq by dt. This term here will become dqu by dx. This term here will become g times a times 1 over gamma, where gamma is the specific weight, times dp dx. This term here becomes GA times the bottom slope, and this term here just becomes GA times SF. Sorry, this should be GA here. So the final expression for our conservation momentum is dq by dt plus d of QU by dx plus G times A times 1 over gamma times the change in pressure with respect to the change in distance minus the bottom slope plus the friction slope. So let me quickly just recap what each of these terms means, and then we can end for today. Believe it or not, we will be using this equation throughout the class. We're going to be using it to derive a lot of the other expressions that we'll be using. This term here, this represents the change in momentum within our control volume. This term here represents the momentum flux through the control volume. And then these three terms here represent our different forces. So which force does this term here represent? Net pressure force, very good. Okay, what force does this bottom slope term here represent? Gravity, very good. So this is the gravitational force. And finally, the friction slope here, unsurprisingly, this is the frictional force. So this is the general expression for the momentum equation. In the next class, we will be using this equation here to formulate the energy equation, which we'll be using extensively throughout the course. Okay, so I will see you all next week on Tuesday, and just keep posted for announcements. Thank you.